Section 9.1, sequences. We started this section back in class. We defined what a sequence is. We gave the notation of a sequence. We gave a few examples. All of these were done in class. We also discussed what we mean by a sequence to converge. Remember, we write this limit as n goes to infinity, an is equal to L, provided the following happens. For any ball centered at L and of radius epsilon, the sequence starts being in that neighborhood, in that ball, or in that interval from a certain rank on. Correct? And a sequence that's not convergent is said to diverge. We talked about this theorem in class. If you have a number L in R bar, so either a real number or plus or minus infinity, and the sequence is given by the image of integer numbers through a function f, then if the function approaches L as x goes to infinity, it's gonna force that the sequence, which is part of the graph of the function, right, is gonna also go to L as n goes to infinity. So this was discussed in class, and the converse doesn't hold. We gave a counterexample for that. All right, we also defined what we mean by a sequence to diverge in a special way, going to plus or minus infinity. We talked about the plus infinity, but the minus infinity can be very much the same. Let's remind ourselves what this means. An goes to plus infinity as n goes to infinity. This means that no matter what number you give me, no matter what positive number m you choose, the sequence starts dominating this number from a certain rank on. So the terms of the sequence start being beyond that number m from a certain rank on. Okay. Still, these were discussed in class. So we have this list of properties of limits. So limit of a sum is the sum of the limits. Limit of a scalar times the term of the sequence is the scalar times the limit of the term of the sequence. In particular, if an they're all 1, you have this equality. And for the product and for the quotient. Okay, there's one also, I think it's on the next page, the pth power. The pth power also as well, right? So the limit of the pth power of the term is the same as the pth power of the limit. And this is as long as the limit exists, right? As long as the sequence is convergent. All right. We also did this example. If an is convergent, so the limit of an exists, then it's the limit as n goes to infinity of an plus 1 is going to match that limit. And we talked about this example also in class. So up to here we took time to establish all of these. And I think the last one we mentioned in class was this theorem, the squeeze theorem, which we know it for, or we used to know it for functions. We can adopt it for sequences. And here are the details. If the limit of a sequence an matches the limit of the sequence cn, if they're both the same, and you have this compound inequality from a certain rank on, meaning you have a third sequence Bn whose terms from this rank n0 onward dominate the terms of an and are dominated by the terms of Cn, then the limit of Bn is going to be that shared limit between An and Cn. Let me prove it for you. There are many ways to prove it. I gave it to you as an extra credit. I think one person just did it, and it was very elegant. I'm going to do it in a different way. Let me go to a new page. Okay, let me go to this page here. All right, so proof of the squeeze theorem. Let's understand what we want first. Let's understand what we want. What we want is, we want to show that this limit happens, right? So we want to show that for any epsilon, there exists a rank from which on the sequence Bn starts being in the neighborhood centered at L and of radius epsilon. So that's what we want. Let me write it for you. So we want that for any threshold epsilon, for any radius epsilon, oh, sorry, maybe I didn't introduce this notation. Okay. So for any epsilon positive, we want to find, a rank n, a natural number n, such that for any rank bigger than this, the distance between Bn and L is not more than epsilon, right? That's what we want to show. Okay. We know that the sequence An is convergent to L, and we know that the sequence Cn is convergent to L. So this means that An starts being in any neighborhood centered at L from a certain rank on, correct? Okay. So I'm going to choose that neighborhood to be centered at L and of radius epsilon over 3. Concretely, this is what I mean. Since An converges to L as n goes to infinity, there exists a rank n1 from which on the distance separating An from L starts being less than epsilon over 3. I can choose any number I wish. I'm choosing epsilon over 3. Why? You're going to see later. Just for things to add up to epsilon. All right, you're going to see shortly. Also, we know that Cn converges to L as n goes to infinity, which means there must exist a number, n2, some rank, from which on the distance separating Cn from L is less than epsilon over 3. So the sequence Cn starts being in the neighborhood centered at L and of radius epsilon over 3. All right. we also know that an is less than or equal to bn, which in turn less than or equal to cn for any number n greater than or equal to n naught, right? This is what they gave us. This is what they gave us in that theorem, right? This is part of the assumption. We know that this compound inequality happens from n0 onward. So I'm rewriting it. Okay. And what am I after? I'm after this. I want to find capital N so that from this rank onward, the distance between Bn and L is no more than epsilon units. What I'm going to choose to be capital N, the one I would like to find, is the largest among all three ni's, between n0, n1, and n2. And you're going to see why. So choose capital N to be defined as the largest, so the maximum between those three ranks, n0, n1, and n2. Obviously, this is a natural number, right? Okay, so from any rank bigger than capital N, this happens, and this happens, right? Because, one more time, this happens for any rank bigger than or equal to n1. This happens here for any rank bigger than or equal to n2. And this happens for any rank bigger than or equal to n naught. Well, if you choose capital N to be the largest among all three, so all three of these properties are going to hold for a rank bigger than capital N. Correct? Okay. Now, I'm going to prove to you that Bn minus L is smaller than epsilon, in absolute value. So Bn minus L in absolute value, that's going to be smaller than epsilon. And you're going to see why. As a first step, I'm going to add and subtract by Bn. So I'm going to get this. I'm going to add and subtract by An. Okay. So what I've done here is I just added and subtracted by the same entity. So certainly these two are the same. Okay. And this is then the same as, because addition is commutative, this is then the same as An minus L plus Bn minus An. Correct? So I just shuffled them around because addition is commutative. So this is the same as An minus L plus Bn minus An. And I hope you recall at this point the triangular inequality that we mentioned in class at the beginning of this section, which says that the modulus, or the absolute value of a sum, I'm going to think about this as one package and this as one package, the absolute value of a sum is less than or equal to the sum of the absolute values. So that's going to be less than or equal to the absolute value of An minus L plus the absolute value of Bn minus An. Correct? What have I done here? I simply used the triangular inequality mentioned at the beginning of this section in class. It's not part of the notes here. Okay? So the absolute value of a sum is less than or equal to the sum of the respective absolute values. On the other hand, what do we know about this? If I choose now n to be greater than or equal to capital N. If I choose now little n to be, so little n that appears in all the discussion here, to be greater than or equal to this number capital N, what do we know about Bn minus An? Well, Bn is greater than or equal to An, so Bn minus An is going to be bigger than or equal to 0. So the absolute value of this is itself then. Let me change the color. So the absolute value of this is itself. Why? One more time. Because for such an n, which is bigger than or equal to n, and n is the largest among all three, so certainly this n is bigger than or equal to n naught. And if you have that, then bn is greater than or equal to an, which means bn minus an is bigger than or equal to 0, which means that the absolute value of this entity is itself, because that guy is already bigger than or equal to 0. Okay. Okay. And so I'm going to write bn minus an as bn. Now I'm going to add and subtract cn. So I can write bn. Actually, how about I do this? For that same n, bn is less than or equal to cn. So if you subtract by an on this side and you subtract by an on this side, you still have this inequality, right? One more time. I'm talking about this upper inequality. Because little n is greater than or equal to capital N, and n is greater than or equal to n naught, so little n is greater than or equal to n naught, and as such, this upper inequality also holds for me. I'm gonna choose it. I'm gonna employ it. Let's subtract by an from both sides. If you subtract by an from both sides, certainly each entity becomes non-negative, and bn minus an is less than or equal to cn minus an. So this guy becomes less than or equal to cn minus an. Correct? And what do you know about cn minus an? You just said it. Cn minus an. Cn is greater than or equal to an, so this is the same as the absolute value of cn minus an. Correct? This is non-negative because cn is greater than or equal to an, so cn minus an is bigger than or equal to 0, so that guy is its own absolute value. So all in all, you get that this pink thing here is less than or equal to that green thing. Okay, so I'm gonna write that. So this is less than or equal to absolute value of an minus L plus absolute value of cn minus an. All right. Now, what I'm gonna do is I'm gonna write cn minus an as cn minus L minus an plus L. This is trivially correct because I just subtracted by L and added by N. So minus L plus L remains 0. And this absolute value is the same as this absolute value. Correct? Okay. And minus an plus L is the same thing as you factor out a negative sign between the two. So if I erase this and write minus, I'm gonna have this as a package, right? This is still the same thing algebraically, right? This is still the same as minus n plus L as we had before. All right, now I'm gonna use the triangular inequality for this this absolute value, and I'm gonna get that this is less than or equal to an minus L plus the absolute value of cn minus L plus the absolute value of an minus L. Correct? And now, what's little n in all this discussion? Little n is greater than or equal to capital N. So it's greater than or equal to n naught, greater than or equal to n1, greater than or equal to n2, which means for this little n, this happens and this happens. This happens here and this happens. Why? Because little n is greater than or equal to capital N, but capital N is greater than or equal to n1 and greater than or equal to n2. So I have this and I have that. let's put it in action here. So the first term is less than epsilon over 3. The second term is less than epsilon over 3. And the last term is less than epsilon over 3. So you get that. This whole thing is less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, because each of these guys is less than epsilon over 3 for this n, and the sum of these three things is simply epsilon. So now, look, we wanted to show that for any epsilon, we can find a rank from which on we get this. And we just showed it. So you take a random epsilon. Okay, let me mention it here. I thought I wrote it. So you take a random epsilon. So let epsilon be positive, be fixed. So you fix a random epsilon, and you were able to find capital N, a natural number, such that from this rank onward, the distance between Bn and L is smaller than epsilon. Then you're done. Let me box the ingredients for you. So for a fixed number epsilon, you're able to choose a number n, a natural number, such that for any n greater than or equal to capital N, Bn minus L is less than epsilon. And this is exactly what it means for Bn to converge to L. And this is what we wanted. And that's what we wanted, right? So that's the proof of the squeeze theorem. Right, next theorem. If the limit of the absolute value of the terms of An is 0, then the sequence An converges to 0. Well, here I'll give you a hint. And the hint is, I hope you pause it and you think about it on your own. So the hint is, An is certainly less than or equal to its own absolute value, right? Because at best, if this is non-negative, then they are the same. If this is negative, this is strictly less than that, right? All right, and on the other hand, this is greater than or equal to minus absolute value of An, right? For the same reason, if An is non-negative, then this guy is going to be equal to that guy. And if An is negative, if An is negative, then the absolute value of An is minus An, so this is going to be An, so they are the same. And if An is non-negative, so the absolute value of An is minus An, which is negative, or non-positive, which is less than or equal to An. So this is true, and this is true for all n, right? Oh, sorry, again, I'm using. By the way, this symbol is, if you've never seen it, this means for all. Okay. Anyway, I'm not gonna write it just to be consistent. So this is true for all n natural numbers. Okay, why this is enough? Because look, if you know that this happens, so that guy goes to 0 and this guy goes to 0, right? Because this is a scalar multiple of that. You can use this property. A scalar multiple, you can push the minus outside, the scalar outside, and you get that the limit of the absolute value of An, right? So that goes to 0 as n goes to infinity by assumption, and that goes to 0 again by assumption as n goes to infinity. So the squeeze theorem kicks in, and it tells us that the middle part has to also go to 0. Okay, so this is trivial if once you observe this and you put squeeze theorem in action. Okay. All right. All right, so I'm going to go quickly over these. Let me remind you before I do any of these exercises or examples, let me just remind you of this theorem here. So this theorem is about if there is a corresponding or a related function whose outputs are the terms of the sequence for integer inputs, then if that thing converges to L, and L, I'm allowing L to be plus or minus infinity, then the sequence is going to go to the same thing. Okay. All right. For this guy, find the limit as n goes to infinity of n divided by n plus 1. There is a related function, function here, which is x divided by x plus 1. Right? The function x divided by x plus 1. And the function x divided by x plus 1 goes to 1 as x goes to plus infinity, correct? It goes to 1 as x goes to plus infinity. And as such, this is going to go to 1. So we cram it here. So if we let the function f of x to be x divided by x plus 1, then the limit as x goes to plus infinity of this function is 1, right? We know this from Calc 1. It's the leading coefficient upstairs divided by the leading coefficient, leading term upstairs divided by leading term downstairs. This is how a rational function behaves at infinity. So you get this. And since fn is equal to n over n plus 1 for all n natural numbers, then the limit as n goes to plus infinity of n over n plus 1 is equal to 1. Why? Because of the theorem I just alluded to just a minute ago, this one, right? So I have that this is 1, L is 1, and Fn is n over n plus 1, which are the terms of the sequence. As such, the sequence is going to go also to 1. Do you agree with me? All right. For this one, it's the same thing. It's very, very close. Now the sequence, the function is going to be x divided by square root of 10 plus x. And that's going to go to x divided by square root of x, which means square root of x. And that's going to go to infinity. So an is going to, at the end of the day, go to plus infinity, which means it's going to diverge. Okay, so it's going to diverge. I'm going to let you write the details. So one more time, the corresponding function is going to be x divided by square root of 10 plus x. Okay. And that function as x goes to infinity is going to go to plus infinity. And as such, the sequence is going to diverge in a special way, which is by going to plus infinity. So an goes to plus infinity. Okay. For problem 5, you have that you want to find the limit as n goes to plus infinity of ln n divided by n. Well, This is plus infinity over plus infinity, so you would like to use L'Hopital, but L'Hopital doesn't apply for sequences, it only applies to functions. Okay, so let's go to the corresponding function, which is ln x divided by x, and use L'Hopital for that, find this limit, and carry over that knowledge to the sequence. So let's do it quickly. So learn as much as we can here. So I'm gonna find, or I'm gonna define a function f of x to be ln x divided by x. Obviously, this is defined for x as long as x is positive. So let's say for x, right, let's say for x positive. And what do we know about the limit as x goes to plus infinity of that guy ln x divided by x? Well, we can use L'Hopital here. We can use L'Hopital and get that the limit as x goes to infinity of derivative upstairs, which is 1 over x, divided by the derivative downstairs, which is 1. And this is 0 at the end of the day, right? As x goes to plus infinity, 1 over x goes to 0. So the limit as x goes to f of x, as x goes to plus infinity, f of x goes to 0. So f of x goes to 0 as x goes to plus infinity, and as such an is fn for all natural numbers n, is going to also go to 0. Correct? By that theorem again. So therefore, that limit as n goes to infinity of ln n divided by n is going to be to 0 by the theorem we just talked about above. All right? Sorry, I'm cramming it here, but I didn't mean to. I wasn't planning to do so, but I decided to just keep the discussion right next to it instead of just going to another page. Okay. Determine whether the sequence an, which is minus 1 to power n, is convergent or divergent. Well, what are the terms of the sequence? When n is 1, that's negative 1. When n is 2, that's negative 1 squared, which is 1. When n is 3, this is back to negative 1. When n is 4, back to 1, right? Negative 1 to power 4 is 1. So this function, this sequence is going to alternate between minus 1 and plus 1. So as such, what do you think the sequence? What do you think the sequence is gonna do? Is it gonna converge or diverge? We discussed this in class. This is certainly is gonna diverge. The limit doesn't exist because there exists no rank from which on the sequence starts being in the neighborhood of any of the two numbers, 1 or negative 1, right? So the limit as n goes to plus infinity of an, in this case, doesn't exist. And this means that an, the sequence an, is convergent. Okay. How about 7? Evaluate the limit as n goes to infinity of minus 1 to power n divided by n. Well, here's the hint. Apply this theorem that we mentioned earlier. We mentioned and we proved earlier. So look at the limit of the absolute value of these terms. So look at the limit of the absolute value of these terms. That's the same as the limit as n goes to infinity of 1 over n, right? And the corresponding function is 1 over x, which goes to 0 as x goes to infinity. So this is going to go to 0 at the end of the day, correct? And what this theorem says, if such a thing happens, then the limit of an as n goes to infinity is also 0. So this forces this conclusion to hold. Correct? Okay. So please label, don't want to label it here because it becomes a little ugly to write, but please label these in your own notes. I mean, refer to what have been used, okay? I'm commenting verbally, but just for you to refer to in the future. So the implication here follows by this theorem. I have that this happens, then that this is going to follow, right? All right. Okay, so the next theorem, it says that if the sequence an converges to L, then the image of that sequence, f of an, is going to also converge to the image of the limit as long as the function is continuous, okay? As long as the function is continuous. If you would like to see the proof of this, please write, just open a forum in the discussion on Canvas and ask me to do so, and I'll be happy to send you a proof. Okay, so the idea here, the image of a convergent sequence under a continuous function is also convergent, but it converges to the image of the limit. Okay, so it converges to the image of the limit. Look at this example here. Pi over n goes to where as n goes to as n goes to infinity? This goes to 0, right? This goes to 0. You can push the pi outside and becomes like this, right? So this is 0. So you have that the limit as n goes to infinity of pi over n is equal to 0. And the sine function is a continuous function at 0. So that's going to be sine of 0. So since sine is continuous at 0, by the theorem just the foregoing theorem, just right here, the limit as n goes to infinity of sine of pi n, f of an, is going to be f of L, and L is 0, right? Which is 0. So you get this result. The limit, so sine pi over n approaches 0 as n goes to infinity. Okay. Example 9. Discuss the convergence of the sequence an equals n factorial. Remember, n factorial means the product of the first n natural numbers for all n greater than or equal to 1 and n natural number. That's same. Okay. All right, fine. Very good. So the sequence, I want to study the convergence of this sequence. Well, okay. So an is n factorial, which means 1 times 2 times 3 times ... times n. divided by n to power n downstairs, which means n times n times. Correct. So how many times downstairs? Exactly n times. How many terms do we have? How many factors, I should say, how many factors do we have upstairs? Well, we have from 1 to n, so we have n factors. How many factors do we have downstairs? N of them. Okay, so that's the same as 1 over n times 2 over n times 3 over n times each one has a partner downstairs, n over n. And now, what can we say about this? Since n keeps going, since n exceeds 2, according to what we're writing here, that number is at most 1. Similarly, this guy, 3 over n, is at most 1. And every guy here is also at most 1. And the last one is equal to 1, which is the same as, which also implies that this is at most 1. So this whole thing, this whole green thing, is less than or equal to 1 times 1 times 1 times 1. So this whole thing is less than or equal to 1 times 1 over n. And 1 over n times 1 is 1 over n. So this whole green thing is less than or equal to 1 over n. Correct? So an is less than or equal to 1 over n. And an is certainly non-negative. Look at the definition of an. It's positive upstairs, positive downstairs. We're talking about n being a positive entity. So an at the end of the day is strictly positive, which I can write also as, if an is positive, certainly an is non-negative, right? All right, so here's what we have. I have that an, okay, is greater than or equal to 0, and at the same time less than or equal to 1 over n. And this is true for all n. For all natural number n. Oh, I wrote this again the same. For all n. Correct? So an is greater than or equal to 0 and less than or equal to 1 over n for all n. Guess what's next? The squeeze theorem is gonna kick in. The squeeze theorem is gonna kick in. I'm not gonna completely write all of the rest. I'm gonna just mention it. As n goes to infinity, this is a constant sequence, so this goes to 0. And as n goes to infinity, this guy also goes to 0. The sequence 1 over n goes to 0. And this is going to force the middle one, an, to go to that common limit between the 0 and the 0, which is 0. So an is going to also go to 0 as n goes to infinity. Okay? So again, let me just say it since I'm not going to write it. We managed to show that an is bounded above by 1 over n for all n, and is bounded below by 0. Since this sequence, the constant sequence, all the terms are 0, goes to 0 as n goes to 0, as n goes to infinity, and 1 over n goes to 0 as n goes to infinity, that's going to force, the squeeze theorem is going to kick in, it's going to force the middle sequence to go also to 0. So that guy, n factorial divided by n to power n, goes to 0 as n goes to infinity. Okay. All right, example 10. For what values of r is the sequence convergent? Okay, let me create a blank page here. Okay. right, so for what values of R is the sequence R to the power n convergent? Let me write here. So this is exercise 10, I believe. Example 10. So the question is for what values of R is the sequence R to power n convergent? All right. Well, do you remember the sequence? Do you remember the function a exponential function ax? Remember this? How does it look? Well, it had two trends. It was either like this. This is where a is bigger than 1. And it was like this, where a is between 0 and 1. Correct? And supposedly here that this, okay, this should pass, the y-intercept is 1, right? Anyway, so so the exponential function whose base is positive and different than 1 have these trends. So if r is bigger than 1, r to power n, as n goes to infinity, is going to be part of the green trend, and that's going to go to infinity. And if r is between 0 and 1, so the sequence is going to be dots on this function, the blue one, and as such, Rn is going to go to 0. Correct? So we can write the following. So from the graphs of the exponential functions, FCT for functions, we have the following. The limit as n goes to infinity of Rn is equal to 0 if the base is between 0 and 1. Right? And it equals plus infinity if the base is greater than 1. So far we know that if the base is bigger than 1, that sequence is going to diverge to plus infinity. And if that base is between 0 and 1, that sequence is going to converge to 0. What happens if r is 1? Well, if r is 1, if r is equal to 1, the limit as n goes to infinity of Rn is equal to 1. Okay. And what happens if r is 0? The limit as n goes to infinity of Rn becomes 0 to power n, which means 0 all the time, which means 0, right? So these are the nicest that R can be. If R is 1, R to power n is 1 no matter what n is, so the sequence Rn becomes 1 all the time. It's a stationary sequence, it's a constant sequence, and as such, the limit is that constant, which is 1. And if R is 0, that's another stationary sequence, which is the 0 sequence. So all the terms are 0, and hence the limit is going to be also that number 0, right? Okay. What if now R is between -1 and 0? If R is between -1 and 0, what can we say? Well, if this happens, then what can we say about the absolute value of R? Well, the absolute value of R becomes between 0 and 1, right? And hence, what is this? The limit as n goes to infinity of the absolute value of Rn. Well, this is the same as the limit as n goes to infinity of the absolute value of R to power n, right? Taking the absolute value of the product of Rn times is the same thing as taking the product of the R copies of the absolute value, right? This is a trivial identity, if you wish. And this is equal to what? Well, the base in this case, this base is, think about the absolute value of R as like a number, A. This base A is between 0 and 1. So if the base A is between 0 and 1, we talked about that case before, then the limit of that thing is going to be 0, right? So one more time, what happened here? All this guy is thought of as the base, and that number is between 0 and 1. And if that number is between 0 and 1, we discussed it before, it was labeled as R before. If that number is between 0 and 1, that the terms of that sequence are going to go to 0, right? They're going to be part of the blue trend. So that's going to be 0. Okay. All right. So what are we left with? We discussed when the base is between 0 and 1, beyond 1, at 1, so we discussed all the positive cases, at 0, when the base is 0, and between 0 and -1. So we still have when R is smaller than or equal to -1, correct? Well, what do you think? When R is -1, what can you say? When R is -1. When R is -1, Rn becomes -1 to power n, right? And that sequence, we discussed it at some point before, probably a couple pages before. It's right there. Right there. Example 6. So an equals -1 to power n did not converge at the time. It was, did I say? Oh, sorry, my bad. I meant diverge at the time. It's divergent, right? I meant divergent, obviously, here. Let me just fix this. So divergent. Sorry about that. Okay. So we said that this is gonna diverge, and hence when R is -1, the sequence is diverging. let me just say that the sequence is divergent. Okay. All right. So what am I left with? I'm left with r being less than or equal to less than -1. If r is less than -1, what can we say about Rn? The sequence Rn. So the sequence Rn is gonna contain the sequence. I mean, think about this. Rn when r is less than -1. Let's say -2, for instance. -2 to power n is gonna contain all the powers of 2 as well, right? 2 to power n. So if r is -2, what's the sequence -2 to power n? The first term is -2. The second term is going to be -2 squared, so 4. And then the third term is going to be -2 cubed, which is -8. And then -2 to power 4, so 16, etc. Correct? So this would be the sequence. And hence, it's going to contain all the powers, the even powers of Rn. Correct? So in other words, that sequence is gonna contain r to power 2n. Am I correct? So all the powers of n, as we said here. R is -2 here. This is -2 squared. This is -2 to power 4. So when n is 1, you're gonna get this. When n is 2, you're gonna get 16, and so on and so forth. All right. And now take a look at this sequence. This sequence here, that's the same as the sequence whose base is r squared to power n. Correct? And if r is less than -1, what can you say about r squared? If r is less than -1, then r squared is going to be greater than 1. Right? If the base r is less than -1, so square the r, you're going to get something bigger than 1, because the squaring function looks like this, right? If this is -1 and r is somewhere less than that, if you square this number, you're going to exceed the image of -1, which is 1. So you're gonna get a number beyond 1. And that's what I said. R squared is going to be greater than 1. Okay. All right. So at this point, I know that this sequence is containing these guys. This is like a subsequence of that. Okay. But what about these guys? A base which is bigger than 1 to power n. A base that's bigger than 1 to power n. That's going to blow up, right? One more time. A base that's bigger than 1 to power n goes to plus infinity as the power n goes to plus infinity. We discussed this case before. So this sequence is divergent, which diverges to to plus infinity. Correct? So what can we say then in this case? If r is smaller than -1, this sequence Rn contains terms which go to plus infinity. So that sequence is not controlled and it's not gonna have a limit. Its terms are not gonna crowd anywhere because it has some terms of that sequence are blowing up. So as a whole, the sequence is not gonna cluster anywhere, and then that sequence is gonna also diverge. So Rn diverges for r less than -1. So in summary, this is what we have. Zoom in. So in summary, this is the result we have. We have that the limit as n goes to plus infinity of Rn is equal to 0 if the absolute value of r is less than 1, right? This is what we showed above. And it's 1 if r is equal to 1. And it's divergent for all other r. And is divergent for all other r. For r that are less than or equal to -1, and for those r that are bigger than 1. Correct? Makes sense? This is so this is the conclusion. And please keep this conclusion in mind. Let me color it for you, so kind of like force you to keep it in mind. Okay. Very good. So Rn is convergent for numbers, for bases that are between -1 and 1, including 1, excluding -1, because the -1 is part of the divergence. So if the base is less than or equal to -1 or bigger than 1, the sequence is going to diverge. Okay. So for those and oops. And for those. Okay. All right, so where are we in the lecture? All right, so we finished example 10. So let me refer you here. See next page. All right. Next definition. We say that a sequence is non-decreasing if the following happens. An is less than or equal to an plus 1. So any term is at most the next term. And this happens for all n and n. So that is to say a1 is less than or equal to a2, and a2 is less than or equal to a3, and a3 is less than or equal to a4, and so on and so forth. Right? So any term is at most the one that it precedes. And it's called non-increasing if the other way happens. If any term does not drop below the next term. A sequence is called monotonic if either it's non-decreasing or non-increasing. Okay, so a monotonic sequence is a sequence that's either non-decreasing or non-increasing. Okay. Example 11, show that the sequence 3 divided by n plus 5 and n divided by n2 plus 1 are non-increasing sequences. Let's create a page for this. And let's do it. So this is example 11. We want to show that the sequence 3 over n plus 5 is non-increasing. Right? So if you call this an, you want to show that an plus 1 is less than or equal to an. This is what we want to show for all n. Correct? Okay. What's an plus 1? Well, an plus 1 is 3 divided by n plus 1 plus 5. And an is 3 divided by n plus 5. Isn't that smaller than or equal to that? Because the denominator is bigger, right? If you increase the denominator, you're decreasing the quotient. So that's certainly less than or equal to this. Since n plus 6 is greater than or equal to n plus 5, right? N plus 6 being the denominator here is greater than or equal to the denominator here, so that's going to happen. Correct? All right. The other part of this exercise was now we want to show that Bn, so this is the second part, we want to show that Bn, which is n divided by n2 plus 1, is non-increasing. So there is, we want to show that an is greater than or equal to an, but Bn is greater than or equal to Bn plus 1 for all n. Correct? That's what we want to show. Okay. All right, let's do it in two ways. First way, how about taking Bn minus Bn plus 1? How about taking this difference? If we manage to show that this difference is greater than or equal to 0, then we get what we want, right? What's Bn? Bn is n divided by n2 plus 1. Now what's Bn plus 1? Replace n by n plus 1, you get n plus 1 divided by n plus 1 squared plus 1, which is equal to same denominator. How about the same denominator being the product of the two? So n2 plus 1 times n plus 1 squared plus 1. So I'm going to have n times n plus 1 squared plus 1 minus n plus 1 times n2 plus 1. Correct? All right. Downstairs is non-negative, no problem. Keep it as ugly as it is, just keep it as is. Upstairs, so downstairs n plus 1 squared plus 1. Upstairs, well, can we do it quickly here? This is n squared times n cubed plus 2n times n is plus 2n squared plus 1, so plus 2 times n minus n times n squared is n cubed minus n times 1, so n, right? N times 1 is n times n squared is n cubed, and n times 1 is n, so we've done this. And then the 1 times n squared, this is negative n squared, and negative 1. All right, so do we have like terms? N cubed minus n cubed. And I'm left with the others. So this becomes n2 plus 1 times n plus 1 squared plus 1 downstairs. Upstairs, I'm going to have 2n squared minus n squared is 1n squared. 2n minus n is 1n plus n. And minus 1, right? Okay. And now what can you say about this guy? This guy here is greater than or equal to, greater than or equal to 1, right? Because n is greater than or equal to 1. We're talking about the sequence which is indexed by natural numbers. So n is at least 1. So n minus 1 is at least 0. And n squared plus 0 is bounded below by 1. So this is at least 1. Correct? All right. So upstairs is at least 1, so positive. And downstairs certainly is positive. So all this guy downstairs is positive. Positive divided by positive is positive. Right? Write it in pink. And if a number is positive, certainly is non-negative. So long story short, Bn minus Bn plus 1 is non-negative. And this is exactly what I wanted. I wanted Bn minus Bn plus 1 to be non-negative. So this does it. This is the first way. The second way is to consider a related function. What's the related function to this guy? It's x divided by x2 plus 1, right? Bn is the output through the function x divided by x2 plus 1, provided you input an integer, a positive integer. So if you consider the function f of x to be x divided by x2 plus 1, Bn are part of the graph of the function f. So you want to show that this sequence is non-increasing, right? So it suffices to show that the function is non-increasing. Make sense? And how do you get information about the monotonicity of the function? You go to the first derivative, calc 1, right? we go to the first derivative. So let's differentiate f. Let's differentiate f. It's quotient rule, so it's 1 times x2 plus 1 minus x times 2x divided by x squared plus 1 squared. Let's do this quickly. X squared plus 1 minus 2x squared. This is going to be 1 minus x squared. 1 minus x squared over x2 plus 1 squared. Okay. What can you say about this quotient if x squared is greater than or equal to 1? Well, if x squared is greater than or equal to 1, then 1 minus x squared is less than or equal to 0. And downstairs is at least 1, so downstairs is positive. So this whole quotient becomes less than or equal to 0, right? So this whole quotient is non-positive if the numerator is non-positive. And this happens when x2 is greater than or equal to 1. x2 being greater than or equal to 1 means that x is less than or equal to negative 1, right? This means that x is in minus infinity to negative 1, union closed, union 1 to plus infinity. Correct? Okay. So this means that f is a non-increasing function for those inputs that are from 1 to infinity. And so f of n is going to be greater than or equal to f of n plus 1 for all n in n. Correct? And what is f of n? What's f of n? It's an. What's f of n plus 1? That's an plus 1. Actually, bn, I think the function, the sequence terms are labeled as bn in this case. So that's going to be bn greater than or equal to bn plus 1, which is what we want. Right? This is what we want. bn greater than or equal to bn plus 1 for all n. All right? So this is another way to show that the sequence is monotonic. Just go to the corresponding sequence and show to the corresponding function and show that this function is monotonic. All right? Okay. That's example 11. Definition. A sequence is said to be bounded above if there exists a number such that all the terms of that sequence are less than or equal to that number. One more time, a sequence is said to be bounded above, provided there exists a certain number that bounds from above all the terms of the sequence for all n. Right? A similar definition can be discussed for boundedness from below. We say that the function is bounded below if there exists a number that's dominated by all the terms of the sequence. And we say that the sequence is bounded above and below. We say that the sequence is a bounded sequence if it's bounded above and below. So if there exists a capital M and a lowercase m, if there are two numbers, little m and capital M, such that they are the lower bound and the upper bound respectively. Okay, such a sequence is referred to as a bounded sequence. Okay. All right, for instance, the sequence AN, which is just n, so all the terms, the term AN is n, is a bounded from below, right? Why? Because AN is bigger than 0. If we talk about a sequence whose index, which is indexed by natural numbers. But this is not bounded from above. Why? Because this blows up, right? The higher n, the higher the index, the higher the output, or the higher the actual term. The sequence AN, which is n divided by n plus 1, is a bounded sequence because n divided by n plus 1 is less than or equal to 1, and the sequence, each term of the sequence is positive. So 0 can be thought of as the lower bound and 1 is the upper bound. We know that not every bounded sequence is convergent. Why? Let's give an example. -1 to power n is a sequence which is a bounded sequence, right? It's bounded below by -1 and it's bounded above by 1. But this sequence is divergent because the terms of the sequence do not cluster anywhere. They don't get crowded anywhere. Well, they get crowded at around 1 and -1, but this would be too many limits, right? A sequence doesn't converge whenever it doesn't have a limit or it has many limits, right? In this case, it has 2 limits. Okay. So what these 2 lines are trying to say is not every bounded sequence is convergent. This is an example. And not every monotonic sequence is convergent. The sequence we just discussed, AN equals n. This is a sequence which is monotonic. It's a non-decreasing sequence, and it's not convergent. It diverges to plus infinity. But what the next theorem is going to tell us is that if a sequence has the 2 characteristics, bounded and monotonic, then it has to be convergent, right? So one of them by itself is not enough to force the sequence to converge. We know of a sequence that's only bounded, this one, doesn't converge, and we know of a sequence that's monotonic, this one, and it doesn't converge. But when both of them are assumed, then the sequence must be a convergent sequence. And this is the next theorem, which is the monotonic sequence theorem. It goes like this. Every sequence that's monotonic, meaning either non-decreasing or non-increasing, and bounded, either bounded above if the sequence is non-decreasing, bounded below if the sequence is non-increasing, then it must be a convergent sequence. Okay, this is a very useful theorem. The proof of this relies heavily on something called completeness axiom of real numbers. Again, this is something I have to talk about, I have to introduce, and this is already too long, this lecture. Still, for those who are interested, if there exists somebody who's interested, I would be happy to explain the proof of this on a different video, but please post this online on Canvas and I'll be happy to do so. Okay, so what's the theorem? The theorem says every sequence that's non-decreasing and bounded above is convergent, and every sequence that's bounded below, that's non-increasing and bounded below is convergent. Long story short, you can summarize it as follows. Every sequence that's monotonic and bounded is convergent. All right. Let's look at this example. Investigate the sequence AN, which is defined by the recursion relation or the recurrence relation, A1 equals 2 and an plus 1 is equal to that. Let's begin by computing the very first few terms. Let me zoom in here. How about we look at a1? Well, we know a1. a1 is 2. How about a2? Well, a2 is given by this recurrence, remember. So when n is 1, this index becomes 2. So this becomes 1/2 times a1, because we took the n to be 1, so that the sum becomes 2, right? So this is a1 plus 6. And what is that? What's a1? a1 is 2. 2 plus 6 is 8. 8 divided by 2 is 4. So a2 is 4. a3 is equal to half a2 plus 6, right? a3, so you want the sum to be 3, so n must be 2. It's half a2 plus 6. And a2 is 4. 4 plus 6 is 10 divided by 2 is 5. Okay. All right, so you do a few. Let me write a few of them. This is 5.5. If you compute it, this is going to be 5.5. a5 is going to be 5.75. a6 is going to be 5.875. Looks like we're getting closer and closer to the limit. That's it. It's already, I mean, I'm on the sixth term, and the function or the sequence starts being closer and closer to that, to something. a7 is 5.9375. a8, the eighth term, is 5.96875. a9, the ninth term, is 5.984,375. All right, I'm not gonna bore you and do more, but the idea here is just those few terms suggest that the sequence is an increasing sequence or non-decreasing, and the terms are approaching 6. I mean, this is what we can observe so far, correct? We're gonna try to show this. We're gonna try to confirm it. We're gonna confirm that the sequence is a non-decreasing sequence and that the sequence is convergent to 6. We're gonna invoke what we call mathematical induction, the principle of mathematical induction. What's principle of mathematical induction? I'm not sure if you've seen it before. If you haven't, I'll try to illustrate it just quickly. So principle. There was a problem, I believe, in the previous homework which uses that. I hope you looked it up online. This is something you should have learned probably, before college algebra. So principle of mathematical induction. How does it go? Well, if you have a statement S, which is in terms of n, so it's a statement that has n, it's in function of n, and n is a natural number. So you have a statement which is in function of n, and the n is indexed under natural numbers. And you want to show the validity of this statement. Okay, so one more time. You have a statement in terms of n, and this n is indexed, or this n is in some natural number, and you want to show that this statement is valid for all natural numbers, what you can do is you show that it's valid for n equals 1. So you show that s of 1 is valid, is true. And you assume that s of n is going to remain valid for all n up to a certain number k. So you assume that s of n remains valid for n less than or equal to k, up to k, right? And then you show that s is valid when n is replaced by k plus 1. So here's the strategy. You want to show that s statement, which is in terms of n, is valid for all n. You can show that s1 is valid, just replace n by 1 and you show its validity. And you assume that Sn is going to remain valid all the way to some rank k. And then, under this assumption, you show that S is gonna be also valid if n is replaced by k plus 1. So which is the next step. If these two bullets, if these two things happen to hold, then what can you say about S of 2? Well, you showed that S of 1 is valid, and you showed that if S of k is valid, then S of k plus 1 is going to be valid. The succeeding one is going to be valid, right? So if S of 1 is valid and you showed that the next one must also be valid, then you're talking about S2 being valid. And now you have S2 being valid, you can reuse this again. You just, the second bullet says, if Sk is valid, then S of k plus 1 is going to be also valid. So if S2, you know that S2 is valid for you, then S3 is going to become valid. And S3 is going to force S4 to be valid, and S4 is going to force S5 to be valid, and hence you're going to get exactly what you want, which is Sn being a valid statement for all n. Okay, so this is the mathematical induction. It operates under these two things. So you have like a baseline, a base statement, S of 1 being valid, the very first one, because n starts at 1, right? The very first one, and then you assume it keeps holding up to a certain rank, and then you show the validity of the following one, which is S of k plus 1. Okay, so this is the idea. And that's what we're going to be using here to show that the sequence, we're going to show that our sequence is increasing or non-decreasing, right? All right, so first we show that an, the sequence an, is non-decreasing. That is, there is a n plus 1 is greater than or equal to an for all n. This is what I want to show, right? So that's my statement. That's my statement, which is clearly in terms of n. So what I want to show is, I want to show when n is 1, this statement is valid. Well, when n is 1, we're talking about a1 being less than or equal to a2. Is it correct? What's a2? a2 is 4, and a1 is 2. So certainly a1 is less than or equal to a2, or equivalently a2 is greater than or equal to a1. Correct? So this is true for n equals 1, since a2 is greater than or equal to a1, right? a1 being 2, we just found it above, and a2 being 4. Now we're gonna assume, so now we pass to the second thing. We're gonna assume that the statement remains true all the way to some rank k. So we assume that up to a certain rank k, this is gonna remain true. Up for all, okay, alright, you know what, I'm gonna assume that this is true up to a certain rank k. So for all n, as long as you replace n by a number that's at most k. So in particular, the kth, so when n is k, that's gonna remain true, so you're gonna get this, right? So you're gonna get this. And what you want to show the validity of s of k plus 1 under this assumption. You want to show that if you replace n by k plus 1, this is going to remain true. And if you replace n by k plus 1, what do you get? That's going to become k plus 1, and that's going to become k plus 1 plus 1, which is k plus 2. Correct? So you want to show that a of a sub k plus 1 is less than or equal to a sub k plus 2. That's what you want to show. All right, let me erase all of these. So we want to show that a of k plus 2 is greater than or equal to a of k plus 1. A sub k plus 1. All right. We have this. Now we want to pass to this. All right, so we have this. What I want to do is, I'm going to rewrite it. And I'm going to add, let me take a look at the sequence. Let me add 6 to both sides. Let's add 6 to both sides. If we add 6 to both sides, the inequality remains true, right? Remember, this is something that I know. This is part of my assumption, the induction hypothesis, or the induction assumption. Now, this is what you want to show. So you want to show the statement when you replace n by k plus 1. All right. So you have this. I add 6 to both sides, nothing changes, and then I'm going to multiply by half. If you multiply both sides by half, you get this. Okay, correct? Multiplying by half amounts to not doing anything to the inequality sign because it's a positive entity. All right, and what is this guy? 1/2 ak plus 6. 1/2 ak plus 6 is 8k plus 1. So this guy on the right side is 8k plus 1. less than or equal to this guy on the left side. What's this guy on the left side? Half ak plus 1 plus 6, half a sub k plus 1 plus 6. So that's going to be a when n is replaced by k plus 1. So k plus 1 plus 1, it's going to be ak plus 2. As wanted, right? This is what you want. It's right there. As wanted. So what does it mean? This means that the statement is true for k plus 1 if you assume that it's true for sk, for when n is k. So what does it mean then? Then, since we showed that a1 is less than or equal to a2, that's going to force a2 to be less than or equal to a3. One more time, this is going to force a3 to be less than or equal to a4. Another time, this thing is going to also force a4 to be less than or equal to a5, and so on and so forth. The sequence then must be a non-decreasing sequence. Correct? So therefore, the inequality an plus 1 greater than or equal to an is true for all n and n by induction. Right? All right. So this is part of the first observation we made. We confirmed it now that the sequence is actually a non-decreasing sequence. Now, the other one is we observed that they're kind of clustering around 6, so it looks like the limit is 6. We need to confirm this as well. What I want to do now is, I know that the function is monotonic, it's non-decreasing, right? So it suffices now to show that the function is bounded above to get the convergence. It suffices to show that the sequence is bounded above to get the convergence. Okay. Next, we show that the sequence is bounded above, and apparently it's going to be bounded above by 6. So an is less than or equal to 6 for all n and n. Right? This is the claim. We're going to also proceed by induction. Remember, induction, you show for the first one, you show that a1 is less than or equal to 6, and then you assume that ak is less than or equal to 6, and you show that ak plus 1 is less than or equal to 6, and then you get it. All right. A1 is certainly less than or equal to 6, right? Why? Because A1 was given to us, it was given to be 2. So the statement holds for n equals 1. Assume that the statement remains valid all the way to a rank k. So assume that this is happening. And we want to show we want to verify that the next term is also bounded above by 6, right? We want to show that this statement is valid when n is replaced by k plus 1. Okay. All right. Same trick. So since ak is less than or equal to 6, this is part of the assumption. If you add 6 to both sides, you get a plus 6 is less than or equal to 6 plus 6, which is 12. And hence, let's divide both sides by 2 or multiply both sides by half. We get half AK plus 6 less than or equal to half times 12, which is 6. Right? Now what is this term? Half AK plus 6. What is it? Half AK plus 6. That's AK plus 1. That's AK plus 1. So what did we show? We assume that this happens. This thing continues to happen all the way to rank K, and we showed it for the following K, for the following rank, which is the K plus first rank. It's right there. We just showed it, and then we got our hands on this, and then this is true then for all n. This is true for all n by induction. So it follows that AK or AN is less than or equal to 6 for all n. Right? So the sequence is a non-decreasing sequence. We showed it. It's a non-decreasing sequence. And it's bounded above. Thus, by the monotonic sequence theorem, the sequence has to converge. Therefore, AN is non-decreasing and bounded above any sequence that's non-decreasing and bounded above is certainly bounded below by the first term, right? So this is certainly a bounded sequence. Thus, by the monotonic sequence theorem, AN converges. So it has a limit. Say that the limit is N. Say that the limit is N. Okay? All right. The question now is, how about we find that limit? How about we find that limit? Because we kind of sense that the limit is going to be 6. Let's actually show that the limit is 6. All right. There's a problem we did in class. Technically, it's... Let me just go back to this. Where is it? Oh, it's right there. Remember this discussion that we did in class? These two exercises? It's very much the same as this one. So we took our time to fully explain it, and we used this equality at the time, if you remember. All right, so I'm going to use something very similar to that. Okay. So you know that that AN goes to L as n goes to infinity. What can you say about AN plus 1? By that exercise that I just highlighted, which we talked about in class, this AN plus 1 also goes to L, right? So AN plus 1 also goes to N, right? So since AN plus 1 is half AN plus 6 for all n, at the limit we obtain the following, that the limit as n goes to infinity of an plus 1 is equal to the limit as n goes to infinity of half an plus 6. And that's the same as this, right? By the exercise discussed in class. So this is the same as the limit as n goes to infinity of an by the exercise we talked about in class. Let me just say here, X exercise. And what is that thing? What is this guy? That's L. So this is equal to L. So that is L, the left side is L, is equal to the half can be brought outside the limit. It's a multiplicative constant. And then the limit of the sum is the sum of the limits. 6 is a pure constant, so it becomes the limit as n goes to infinity of an, which is L. So that becomes half times L plus 6. So again, how did I get that? The right side, half is a multiplicative constant. I'm using the laws that we mentioned on probably, what is it? So I'm talking about the laws, the very last laws we mentioned, the properties of limits we mentioned in class last time we met. The half can be brought outside, and the limit of a sum is the sum of the limits. And I'm using also that the limit of a constant is that constant. So I'm using these guys. So the half for the C, the sum here, an and 6, split them up, and limit as n goes to infinity of 6 is 6 by this guy. Okay. And you get that thing. All right, and this is easy to solve. If you multiply through by 2, you get 2L equals L plus 6, which means L is 6. Right? So that limit is actually 6. So conclusion, the limit as n goes to infinity of an is equal to 6. As we predicted, correct? All right, so this is the end of this section. I'll see you in the next one.